Every story has a beginning, but the universe's beginning is unlike any story ever told. It is not the birth of a star or a galaxy or even matter itself. It is the moment when space, time, energy, and the laws that govern reality all came into existence at once. For as long as humans have looked up at the night sky, we have wondered where everything came from, why the universe exists, why it has structure instead of chaos, and why, against overwhelming odds, it allows stars, planets, life and consciousness to emerge. In the last century, science uncovered something extraordinary. The universe has a history, and that history can be traced backward through galaxies, through atoms, through energy itself toward a single beginning. This is not a story of explosions or fireworks. It is a story of expansion, of emergence, of simplicity giving rise to complexity. This is the story of the Big Bang, not just as an idea, but as the origin of everything we have ever known. And to understand it, we must begin where there was no space, no time, and no universe at all. Before the universe began, there was no light to see, no sound to hear, no space to move through. There was no darkness either, because darkness, like light, requires space, and space did not yet exist. This is not easy to imagine. The human mind is shaped by experience, by distance, by time, by change. But at the very beginning, none of these existed. There was no before, no ticking clock waiting to start, no empty stage waiting for the universe to appear. Time itself had not yet taken its first step. When we ask how the universe began, we are asking one of the deepest questions ever formed by human thought. Where did everything come from? Why is there something rather than nothing? And how did existence itself begin? For thousands of years, this question lived in myths, stories, and philosophy. Only recently has science been able to trace the universe's history all the way back to its earliest known moment. That moment is what we call the Big Bang. But the Big Bang is often misunderstood. It was not a giant explosion sending matter outward into empty space. There was no center point, no surrounding void. Instead, the Big Bang was the moment space itself came into existence. Every distance we measure today between stars, between galaxies, between atoms was once zero. Not small, not compressed, but undefined, because distance itself had no meaning. To understand this, we must let go of everyday intuition. The universe did not begin in time. Time began with the universe. There was no earlier moment that led to it, no countdown, no build-up. The beginning was not an event inside a timeline. It was the start of the timeline itself. Imagine rewinding the universe backward. Galaxies drift closer together. Stars merge into glowing clouds. Atoms lose their structure. Matter dissolves into energy. The universe becomes hotter, denser, more uniform. As we go farther back, our equations continue to work, until suddenly they don't. At a certain point, our understanding of physics breaks down. Not because the universe stops making sense, but because we have reached the edge of what our current knowledge can describe. That edge marks the beginning. At that moment, all the matter and energy that would ever exist was contained within an unimaginably small state, not squeezed into space because space itself had not yet emerged. The universe was not somewhere. The universe simply was. This is where certainty ends and mystery begins. We cannot see beyond this point. We cannot measure before it. We can only observe the consequences, the faint glow left behind, the expansion that continues today, the structure written into the cosmos. The universe carries the memory of its birth, and even now, billions of years later, space is still stretching. Galaxies continue to move apart. Light continues its long journey. The echo of the beginning still whispers through the universe. This is where our story starts. Not with stars, not with galaxies, not with planets or life, but with the moment when space and time themselves took their very first breath. When most people hear the words Big Bang, they imagine a massive explosion, a single point detonating violently, throwing stars and galaxies outward into an empty universe. But this picture is misleading. The Big Bang was not an explosion in space. It was an expansion of space. An explosion happens at a location. It has a center. It pushes matter outward into surrounding space. The Big Bang had none of these qualities. There was no center point, no outer edge. no empty space waiting beyond it. Every point in the universe was once compressed together, and when expansion began, every point moved away from every other point at the same time. This means that from any galaxy today, the universe appears to be expanding outward, and that is exactly what we observe. But this does not mean that any galaxy is at the center. There is no special location, no privileged point of origin. The universe expands uniformly, the same in every direction. A useful analogy is the surface of a balloon. Imagine tiny dots drawn on the balloon's surface. As the balloon inflates, the dots move farther apart. From the perspective of any single dot, all the others appear to be moving away. Yet none of the dots is the center of expansion. The expansion happens everywhere at once. In the case of the universe, there is no balloon surface and no surrounding air. Space itself is what stretches. Distances grow, not because objects are moving through space, but because the space between them is expanding. This expansion began with the Big Bang, and remarkably, it has never stopped. Another common misconception is that the Big Bang created matter by blasting it outward. In reality, the earliest universe was filled with energy. Matter came later. As the universe expanded and cooled, energy transformed into particles. These particles eventually formed atoms, and atoms formed stars and galaxies. But at the beginning, there were no familiar objects at all. There were no stars to explode, no planets to shatter, no particles to scatter, only energy, governed by laws far more extreme than anything we experience today. The Big Bang is not an object. It is not a place. It is not something we can point to on a map of the universe. It is a moment in time, the moment when space began to expand. And because time itself began at that moment, asking what happened before the Big Bang may not have a meaningful answer. It is like asking what is north of the North Pole. The question assumes a direction that no longer applies. This does not mean curiosity ends here. Physicists explore ideas such as quantum fluctuations, cyclic universes, and multiverse theories. But so far, all confirmed observations point to one fact. The universe has a finite age. It had a beginning. We know this because the universe is expanding. When we look at distant galaxies, their light is stretched to longer wavelengths. This redshift tells us they are moving away from us. And the farther away a galaxy is, the faster it appears to be receding. If we reverse this expansion mathematically, everything comes closer together. Eventually, distances shrink to zero. That convergence marks the beginning. The Big Bang is not just a theory based on imagination. It is supported by multiple lines of evidence: the expansion of space, the abundance of light elements, and the faint afterglow of radiation left behind from the early universe. Together, they form a consistent story. A story that tells us the universe was once hotter, denser, and more uniform than it is today. A story that leads inevitably to a beginning. The Big Bang was not chaos. It was not random destruction. It was a precise unfolding of physical laws at the birth of reality itself. And to understand it fully, we must go even deeper. We must examine the moment when time itself began, the instant known as time zero. Time is so deeply woven into our experience that imagining its absence feels impossible. Every thought we have exists in a sequence. Every memory points backward. Every expectation points forward. Yet the universe has not always had time. Time itself had a beginning, and that beginning is known as time zero. Time zero is not a moment that came after something else. It is the first moment. The point at which the universe's clock started ticking for the very first time. There was no earlier second, no previous instant. The concept of before does not apply here. In everyday life, time is a background we rarely notice. It flows continuously, uninterrupted, seemingly independent of the universe itself. But in modern physics, time is not separate from space. Together they form a single structure called space-time. Space-time is flexible. It can stretch, bend, and curve. Gravity is not a force pulling objects together, it is the curvature of space-time itself. Mass tells space-time how to curve, and curved space-time tells matter how to move. At the beginning of the universe, space-time did not yet exist. There was no grid, no dimension, no fabric to bend or stretch. The birth of the universe was also the birth of space-time. Space and time emerged together. This is why asking what happened before the Big Bang is so difficult. The question assumes time already existed, but time itself began at the Big Bang. Without time, there is no sequence of events, no cause followed by effect, no earlier state to transform into a later one. Some theories attempt to describe a deeper layer of reality beneath space-time. Quantum gravity, string theory, and loop quantum cosmology suggest that space-time may emerge from something more fundamental. But these ideas remain untested. For now, the earliest moment we can meaningfully describe is time zero. At time zero, the density of the universe was extreme, so extreme that our equations predict infinite density and temperature. This point is called a singularity. A singularity is not necessarily a physical object. It is a signal that our current theories are incomplete. The mathematics tells us that something extraordinary happened, but it cannot yet tell us exactly what. What we do know is that immediately after time zero, the universe began to expand, and as it expanded, time began to flow. One moment followed another. Change became possible. This flow of time is not the same everywhere. Time moves differently depending on speed and gravity. Clocks run slower near massive objects. Time itself stretches as space expands. Even today, time is still unfolding along with the universe. Every second that passes is another step away from that first moment. The universe does not move through time. Time moves with the universe. They are inseparable. When we look at the night sky, we are seeing light that left its source millions or billions of years ago. In this sense, astronomy is a form of time travel. The farther we look, the farther back in time we see. The oldest light we can observe comes from a time just after the universe became transparent. It is the afterglow of the Big Bang, a frozen snapshot of the universe when it was still young. This ancient light tells us that time truly did have a beginning, that the universe has a history, a story, and that story starts at time zero. But time zero was only the first instant. What followed was a universe changing at an unimaginable speed. The first fraction of a second after time zero was unlike anything the universe would ever experience again. This was a reality far beyond stars, far beyond atoms, far beyond anything familiar. The universe was unimaginably hot, dense, and energetic, so extreme that the laws of physics we rely on today were not yet fully formed. In this earliest instant, the universe was filled with pure energy. There were no particles in the way we know them, no protons, no neutrons, no electrons. Matter had not yet taken shape. Energy dominated everything. Temperature is a measure of motion, and in the early universe, motion was absolute. Energy surged everywhere, vibrating at levels so intense that stable structures could not exist. Any particle that briefly formed was immediately destroyed by collisions with surrounding energy. Creation and annihilation happened constantly, everywhere at once. During this time, the fundamental forces of nature were not separate. Today, we recognize four forces: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. But in the first fraction of a second, these forces were unified. They were different expressions of a single fundamental interaction. As the universe expanded and cooled, this unity began to break. Like ice forming from water, symmetry shattered. Forces separated from one another. Each took on its own identity, its own role in shaping reality. Gravity was the first to emerge. Though incredibly weak compared to other forces, gravity would eventually shape the large-scale structure of the universe. Galaxies, stars, and planets would one day form because gravity began asserting itself in these earliest moments. Next came the separation of the strong nuclear force. This force would later bind quarks together to form protons and neutrons. Without it, atomic nuclei could not exist. Matter itself would be impossible. The universe was still far too hot for particles to settle into stable forms. But the foundations of reality were being laid. The rules were taking shape. Time moved forward. The universe continued expanding. And with expansion came cooling. Even a tiny decrease in temperature had profound consequences. At around a trillionth of a second after the beginning, conditions finally allowed some particles to persist. Quarks, the fundamental components of matter, began to appear. They did not exist peacefully. They collided, merged, and annihilated in pairs with their antimatter counterparts. For every particle of matter, a corresponding particle of antimatter formed. When matter and antimatter meet, they destroy each other in a burst of energy. And in the early universe, this happened constantly. Yet, for reasons we still do not fully understand, there was a slight imbalance, a tiny excess of matter over antimatter. This difference was incredibly small, about one particle in a billion. But it was enough. When most matter and antimatter annihilated each other, that tiny surplus of matter remained. Every star, every planet, every living being exists because of this imbalance. As the universe cooled further, quarks began to combine. 3 quarks joined to form protons and neutrons. For the first time, components of atomic nuclei existed. Still, atoms themselves were far in the future. The universe was now filled with a dense, hot soup of particles and radiation. Protons and neutrons collided constantly. Electrons raced freely. Light could not yet travel far. Photons were trapped, bouncing endlessly between charged particles. Space was expanding rapidly, but the universe remained opaque. There was no clear direction, no visible structure, only motion, energy, and change. Despite the chaos, the universe was remarkably uniform. Temperature and density were nearly the same everywhere. This uniformity would later become one of the strongest clues to what happened next. Because the universe was so smooth, so evenly balanced, something must have occurred to spread energy evenly across vast regions of space. This leads us to one of the most important ideas in modern cosmology, a moment that reshaped everything. A brief but dramatic phase known as cosmic inflation. Inflation would stretch the universe at an extraordinary rate, faster than the speed of light, not through space, but of space itself. It would explain why the universe looks so uniform, why distant regions share the same properties, and why tiny fluctuations later grew into galaxies and stars. But inflation did not happen immediately. It emerged from the conditions created in this first fraction of a second, from the energy, the expansion, and the symmetry breaking that defined the universe's earliest moments. These first instants were not just a beginning, they were a blueprint. They determined the structure of everything that would come later. In the earliest moments of the universe, something extraordinary happened, something so powerful that it shaped the entire cosmos we see today. This event is known as inflation. Inflation was not a slow expansion, it was sudden, violent in scale, and incredibly brief. In a tiny fraction of a second, the universe expanded exponentially. Regions of space smaller than an atom were stretched to cosmic proportions. To understand inflation, we must first understand how expansion works. Nothing moved through space faster than light. Instead, space itself expanded. Distances grew so rapidly that regions once connected were suddenly separated by vast cosmic gulfs. Inflation explains one of the greatest mysteries in cosmology. Why does the universe look almost the same in every direction? No matter where we look, the temperature of the universe is nearly identical. Without inflation, distant regions would never have had time to exchange information or energy. They should look different, but they don't. Inflation provides the answer. Before inflation, the universe was small enough for all regions to interact. Energy and temperature were evenly distributed. Then inflation stretched this uniformity across the entire observable universe. This is why the cosmos appears smooth on the largest scales. Why space has the same basic properties billions of light-years apart. Inflation also explains why the universe appears geometrically flat. Not flat like a sheet of paper, but flat in the sense that parallel lines remain parallel over enormous distances. Without inflation, space would be strongly curved. But observations show that the universe is remarkably close to perfectly flat. During inflation, quantum fluctuations, tiny random variations in energy, were stretched along with space. These fluctuations were incredibly small, but inflation magnified them to astronomical scales. These stretched fluctuations became the seeds of structure. Slightly denser regions would later attract more matter. Over billions of years, they would grow into galaxies, clusters, and the vast cosmic web. In this way, inflation planted the blueprint for everything we see today. Every galaxy began as a microscopic ripple in the early universe. Inflation did not last long. It ended almost as quickly as it began, but its effects were permanent. When inflation stopped, its energy was released into the universe. This process, called reheating, filled space with particles and radiation. The universe became hot again, though not as hot as at the very beginning. Now, conditions were right for matter to form in stable ways. Inflation also explains why we observe no edge to the universe. The observable universe is only a small part of a much larger whole. Beyond what we can see, space likely continues, perhaps infinitely. Some versions of inflation suggest that it never fully stops, that inflation continues elsewhere, creating countless universes, a multiverse, each universe with its own properties. These ideas remain speculative, but inflation itself has strong observational support. Its predictions match what we see in the cosmic background radiation. They match the distribution of galaxies. They match the universe's geometry. Inflation transformed a tiny hot beginning into a vast, structured cosmos. Without it, the universe would be unrecognizable. And yet inflation is still not fully understood. We do not know exactly what caused it. We do not know what field or mechanism drove it. This mystery reminds us that even our best theories are incomplete, that the universe still holds secrets from its earliest moments. But one thing is clear: inflation was a turning point. It smoothed the universe. It seeded structure. It set the stage for everything that followed. After inflation ended, the universe entered a new phase, a phase where energy cooled, particles stabilized, and reality began to take a more familiar form. When inflation ended, the universe was vast, hot, and filled with energy. But it would not remain this way. Expansion continued. And as the universe expanded, it began to cool. This cooling marked a turning point, the moment when reality started to take on a familiar form. Temperature is a measure of energy. In the early universe, energy was everywhere, but as space stretched, that energy spread out. With each passing moment, the universe became less intense, less chaotic, and more structured. As temperatures dropped, energy could no longer dominate completely. It began transforming into matter. Particles that once appeared only briefly could now survive. The universe was ready to build its first lasting components. Quarks, which had previously existed in a violent sea of energy, began to settle. They combined into stable groups. 3 quarks formed protons and neutrons, the core building blocks of atomic nuclei. For the first time, matter had a foundation. But the universe was still far too hot for atoms to exist. Electrons moved too quickly to bind to nuclei. Any attempt at structure was immediately torn apart by surrounding energy. Still, progress continued. As seconds passed, protons and neutrons collided and fused. This process is known as primordial nucleosynthesis. In the first few minutes after the Big Bang, the universe acted like a massive nuclear furnace. Hydrogen nuclei formed first, then helium. Tiny traces of lithium also appeared. These were the only elements the early universe could produce. Everything heavier would come much later, inside stars. This moment fixed the universe's elemental makeup. Even today, about 3/4 of all normal matter is hydrogen. Almost all the rest is helium. This precise balance is one of the strongest confirmations of the Big Bang theory. As the universe continued to expand, fusion reactions slowed, temperatures dropped further, the nuclear furnace shut down. The universe entered a long, quiet phase. Space was now filled with a hot plasma of charged particles. Protons and atomic nuclei floated freely. Electrons raced among them. Light was still trapped. Photons constantly collided with charged particles, unable to travel far. The universe glowed intensely, but there were no stars, no galaxies, no darkness. Only a uniform, radiant fog stretching endlessly in every direction. Gravity was present, but its effects were subtle. Tiny differences in density left behind by quantum fluctuations during inflation began to matter. Regions that were slightly denser started attracting more matter. The seeds of structure were quietly forming, but change was slow. The universe was still too hot and too smooth for dramatic structure to emerge. Millions of years would pass before gravity truly took control. This era of cooling was essential. It allowed matter to stabilize. It set the conditions for light to one day travel freely. It prepared the universe for its next great transformation. Eventually, electrons would slow down enough to bind with nuclei. Atoms would form. Light would finally be released. The universe would become transparent. But that moment had not yet arrived. For now, the cosmos remained dense, hot, and filled with glowing plasma. Still, the universe was changing. Every second, space expanded. Every second, temperatures fell. Every second, the universe moved farther from its fiery beginning. This cooling phase was not dramatic. There were no explosions, no sudden events, just a steady, inevitable transformation. And yet, without this quiet cooling, nothing else would be possible. No stars, no planets, no life. For hundreds of thousands of years after the Big Bang, the universe was filled with light. Yet paradoxically, it was impossible to see. This was an era where light existed everywhere, but could not travel freely. The universe was bright and completely opaque. At this stage, space was filled with a hot plasma. Protons and atomic nuclei floated freely. Electrons raced endlessly between them. Together they formed a dense, charged fog. Light, in the form of photons, was constantly emitted, but these photons could not move far. Each time a photon tried to travel, it collided with a charged particle. It was scattered, absorbed, and re-emitted in a different direction. This happened again and again. A photon's path was a random, endless zigzag. Even after thousands of years, light could move only a short distance. The universe was effectively opaque. There were no shadows, no clear direction, no stars or galaxies to illuminate space. The glow was uniform. Every region of the universe looked nearly identical to every other. This period is known as the photon-baryon era. It was a time when matter and light were tightly coupled. Neither could move independently. Despite the uniformity, tiny variations existed. Regions slightly denser than average had stronger gravity. They pulled in more matter. They also affected how photons moved. These subtle differences would leave an imprint that we can still observe today. As the universe expanded, it continued to cool. Electrons gradually lost energy. They moved more slowly. Their interactions with nuclei became less violent. Eventually, the universe reached a critical temperature, low enough for electrons to bind to protons. This process is called recombination. Despite the name, this was actually the first time electrons combined with nuclei to form neutral atoms. Hydrogen atoms formed in enormous numbers. For the first time, matter became electrically neutral. This changed everything. Neutral atoms do not scatter light the way charged particles do. Photons were no longer trapped. They could finally travel in straight paths across vast distances. At that moment, the universe became transparent. Light was released. The fog lifted. This release of light marked the end of the universe's earliest era. Photons that had been trapped for hundreds of thousands of years were suddenly free. They began a journey that continues even today. Those photons are still traveling. They have been stretched by the expansion of the universe. Their wavelengths have grown longer. What was once brilliant light is now faint microwave radiation. This ancient light is called the cosmic microwave background. It is the oldest light we can observe. A snapshot of the universe when it was just 380,000 years old. The cosmic microwave background is almost perfectly uniform, but it contains tiny fluctuations, minute temperature differences that reflect the earliest structures in the universe. These fluctuations are the seeds of galaxies. They show us where matter was slightly denser, where gravity would later pull matter together. In this way, light carries a record of the universe's infancy, a fossil imprint written across the sky. When we study this radiation, we are not just observing light, we are observing time itself, a message sent from the young universe to the present. The era of trapped light had ended, but the story was far from over. Now, the universe would enter a long period of darkness, a time before stars, a time before galaxies, a time known as the Cosmic Dark Ages. When light was finally released, the universe changed forever. After hundreds of thousands of years of confinement, photons were free to travel. They streamed outward in every direction. carrying with them a perfect record of the universe at that moment. This was not a sudden explosion of light. There were no flashes or bursts. Instead, the universe quietly became transparent. The fog lifted, space cleared. For the first time, light could move unhindered across the cosmos. The universe entered a new era, one defined by visibility. The photons released during this moment spread out as the universe expanded. Their energy slowly decreased, their wavelength stretched. What began as visible and infrared light gradually shifted into microwaves. Today, this ancient light fills all of space. It arrives at Earth from every direction. It is faint, cold, and remarkably uniform. This radiation is known as the cosmic microwave background. It is the afterglow of the Big Bang, a whisper from the universe's youth. Discovered accidentally in 1965, the cosmic microwave background provided powerful confirmation of the Big Bang theory. It matched predictions with astonishing precision. Tiny temperature variations within this radiation revealed something extraordinary. They showed that the early universe was not perfectly smooth. There were small differences in density, just 1 part in 100,000. These tiny imperfections would shape everything to come. Over time, gravity would amplify them. Denser regions would attract more matter. Lighter regions would become emptier. From these subtle beginnings, the large-scale structure of the universe would emerge. Filaments, voids, clusters of galaxies, all traced back to these early fluctuations. The cosmic microwave background is more than just light. It is a map, a record of conditions when the universe was young. By studying its patterns, scientists have learned the age of the universe, its composition, and its geometry. They have measured how much matter exists, how much dark matter is present, and how much energy drives cosmic expansion. No telescope pointed at stars could reveal this information. Only this ancient light could tell the story. The release of light marked the end of the universe's earliest chapter, but it also marked the beginning of a long, quiet era. With light free to travel, the universe grew dark. Stars had not yet formed. Galaxies did not exist. Space was filled with neutral gas and faint radiation. This period is known as the Cosmic Dark Ages. It lasted for hundreds of millions of years. During this time, gravity worked patiently. Matter slowly gathered. Invisible structures formed. The universe prepared for its next great transformation. Even now, billions of years after the Big Bang, the universe still carries the memory of its beginning, not as a story written in words, but as patterns etched into space itself. The universe remembers how it began, and it shows us everywhere we look. The most obvious echo is expansion. Space is still stretching. Galaxies are still moving apart, not because they are flying through space, but because the space between them continues to grow. When astronomers observe distant galaxies, they see their light shifted toward redder wavelengths. This redshift increases with distance. The farther away a galaxy is, the faster it appears to be receding. This relationship is known as Hubble's law. It tells us that the universe is expanding uniformly. And if we trace this expansion backward, we find a time when everything was closer together, a beginning. The expansion of the universe is not slowing down. In fact, it is accelerating. Something unseen is pushing space to expand faster over time. This mysterious influence is called dark energy. Dark energy does not clump. It does not form stars or galaxies. Instead, it acts uniformly across space, driving cosmic acceleration. Though we do not yet understand what dark energy truly is, its effects are unmistakable. It shapes the future of the universe. Another echo of the beginning lies in the distribution of galaxies. When astronomers map the universe, they see a vast cosmic web. Filaments of galaxies stretch across enormous distances. Between them lie vast voids. This structure reflects the tiny fluctuations present in the early universe, the same fluctuations seen in the cosmic microwave background. Over billions of years, gravity amplified these differences. Matter flowed into denser regions. Galaxies formed along invisible scaffolding of dark matter. Dark matter does not emit light. It cannot be seen directly, but its gravitational influence is essential. Without dark matter, galaxies could not form as we observe them. Another echo of the Big Bang is elemental abundance. The universe still contains the same proportions of hydrogen and helium created in its first minutes. Stars rearrange matter, but the overall balance remains. Even the temperature of space reveals the universe's history. Space is not truly cold. It has a faint temperature of just a few degrees above absolute zero. This heat comes from the cosmic microwave background, the afterglow of creation. Every direction we look, this radiation surrounds us. It is a reminder that the universe was once hot and dense everywhere. The Big Bang is not just a theory about the past, it is a framework that explains the present, the expansion we measure, the light we observe, the structure we map. All are consequences of that first moment. By studying these echoes, scientists refine our understanding of the universe's age, its composition, and its fate. Each new observation adds clarity, but it also raises new questions. What is dark energy? Why does matter dominate over antimatter? Why does the universe have the properties it does? The echoes of the beginning do not give us all the answers, but they guide us. They connect the present to the moment when time began. When we observe the universe, we are not passive observers, we are part of the story. The atoms in our bodies were shaped by cosmic history. Our existence is linked to the universe's expansion. The Big Bang is not distant, it is ongoing. Its effects are still unfolding. The Big Bang is often described as a scientific theory, a set of equations, a model of cosmic history, but its meaning goes far beyond mathematics. The Big Bang reshapes how we understand existence itself. It tells us that the universe has a history, that it was not always as it is now, that space, time, and matter came into being together. This challenges ancient assumptions. For much of human history, the universe was thought to be eternal, unchanging, without beginning or end. The discovery of the Big Bang revealed something astonishing. The universe is dynamic, it evolves, it grows. This realization changes how we see our place in the cosmos. We are not living in a static universe. We are part of a story that has been unfolding for billions of years. Every atom in your body was forged through cosmic processes that began with the Big Bang. The hydrogen in your cells formed in the universe's first minutes. Heavier elements were created later, inside stars. We are made from the universe's history, not separate from it, not observers standing apart, but participants. The Big Bang also reveals how simple beginnings can lead to extraordinary complexity. From nearly uniform energy emerged galaxies, stars, planets, and life. This process did not require intention or design. It followed physical laws. And yet, the result is a universe capable of producing awareness. This raises profound questions. Is consciousness an accident, or an inevitable outcome of cosmic evolution? Does the universe observe itself through us? Science does not yet have answers, but the Big Bang invites us to ask these questions with humility. It also reminds us of our shared origin. Every human, every animal, every living thing comes from the same cosmic beginning. Our differences are small when compared to our common history. We all trace our existence back to the same first moment. The Big Bang places our lives within a vast context. Our worries and ambitions are real and meaningful, but they exist within a universe billions of years old and unimaginably large. This perspective can be humbling, but it can also be comforting. We are not alone in a chaotic universe. We are part of a structured, evolving cosmos. The laws that govern stars also govern us. The same forces shape galaxies and thoughts. Understanding the Big Bang does not diminish meaning. It deepens it. It connects us to something far greater than ourselves. The story of the universe does not begin with stars. It begins with a moment when there was no space to hold them, no time for them to shine, a moment when everything we would ever know was still becoming. From that first instant, the universe unfolded with quiet precision. Energy cooled, matter formed, light was released. And over billions of years, structure emerged from simplicity. Galaxies gathered, stars ignited, planets took shape. And on at least one small world, the universe learned to observe itself. When we look up at the night sky, we are not seeing something distant. We are seeing our own history. The light reaching our eyes began its journey long before we existed. It carries with it the memory of creation. The Big Bang was not an ending, it was an opening, a beginning that continues even now. Space is still expanding, time is still unfolding, the universe is still becoming. We often search for meaning in small moments, but meaning also exists on cosmic scales, in the fact that the same laws governing galaxies also shape our lives. Every breath we take is connected to the universe's first moments. Every atom in our bodies was born from cosmic processes set in motion at the beginning of time. We are not separate from the universe. We are expressions of it, temporary but deeply connected. As this journey comes to an end, the universe continues, beyond our questions, beyond our understanding, expanding into the unknown. And perhaps that is its greatest gift. Not answers but wonder, not certainty but curiosity. From a single beginning, an endless story emerged. And for a brief moment in time, we are part of it. As we reach the end of this journey, it's important to remember something simple, yet profoundly powerful. The universe did not begin small so that your life could be small. From the very first moment, from the birth of space and time, everything has been expanding. And so have you. The universe is not static, it never has been. It moves, it grows, it transforms. And you are made of the same energy, the same atoms, the same laws, the same momentum. Every challenge you face, every dream you carry, every idea that feels bigger than you exists, because the universe itself has always favored possibility. Nothing in existence is accidental, not the stars, not the galaxies, not you. When the universe began, it did not know where galaxies would form. It did not know where life would appear. And yet it trusted the process. It allowed expansion. It allowed uncertainty. It allowed becoming. And that same permission exists for you. If you put your mind to something, if you focus your energy, if you move with intention, things begin to align. Not always instantly, not always perfectly, but always meaningfully. The universe responds to motion. It responds to belief. It responds to direction. Even the smallest step forward changes the trajectory of everything that follows. There are moments in life when the path feels unclear, when timing feels off, when progress feels slow. But even in those moments, nothing is wasted. Stars do not form instantly. They collapse slowly, patiently, under pressure, and one day they ignite. So if you feel pressure in your life, if you feel challenged, if you feel stretched, it may not be a sign to stop. It may be a sign that something powerful is forming. Everything is possible in life, not because life is easy, but because the universe is infinitely creative. The same force that shaped galaxies is shaping your future. The same energy that fuels stars moves through your thoughts, your choices, your actions. You are never disconnected from the universe, even when you feel lost, even when you feel unsure. Alignment is not about perfection. It's about direction. When your intentions are honest, when your heart is open, when your actions match your values, the universe listens. Opportunities begin to appear. People arrive at the right time. Paths open where there were none before. Not by coincidence, by alignment. The stars are not random. They follow patterns, cycles, rhythms. And so does your life. There are seasons for growth, seasons for rest, seasons for transformation. Trust each one. If something leaves your life, it is making space. If something takes time, it is gaining strength. If something feels uncertain, it is still unfolding. The universe does not rush, and yet everything arrives exactly when it needs to. You are supported in ways you cannot always see, by timing, by energy, by unseen connections. When you choose hope over fear, action over doubt, belief over limitation, you move closer to the version of yourself that already exists in potential. Nothing you dream of is placed in your mind by accident. Ideas are invitations. Visions are messages. Desires are signals pointing you forward. The universe does not tease. It does not show you possibilities without also giving you the ability to reach them. Sometimes the journey is not about becoming more. It's about remembering who you already are. You are capable. You are guided. You are aligned, even when it doesn't feel like it. When you look up at the night sky, remember this. Those stars are ancient. They have witnessed the birth of time, and still they shine. If they can burn for billions of years, you can endure your moment of doubt. If the universe could emerge from a single point of energy, You can build a life from a single decision. Everything works together. Even setbacks, even delays, even endings. Nothing is truly lost. It only transforms. And just like the universe, you are always becoming, always expanding, always moving forward even when it feels still. Trust yourself. Trust the timing. Trust the process. You are exactly where you need to be to take your next step. The universe is not against you. It never has been. It is responding to you. Every thought you nurture, every action you repeat, every belief you strengthen shapes your reality. So choose wisely. Choose growth. Choose patience. Choose faith in yourself, because the universe believes in motion, and it believes in you. As this story comes to a close, remember this was never just about the universe. It was about your place within it. From the first moment of time to this very second, everything has been leading here. And the story doesn't end now, it continues through you. Comment, like, and subscribe on the Veil of the Universe for more stories about the universe and the frequency.